It's a dev demo Instrumentu app for traces, Tracing 101. And it's me, Sergey Konzhelev from Google.
Hi, and I'm Yoshi Yamaguchi. I'm a developer advocate for Google Cloud.
Today's session will have two parts. First, we will cover some main concepts of tracing, and then we go more into coding. This is Tracing 101, so we will only cover basics and wouldn't cover any gotchas beyond getting started. But we hope you still get a lot of value from that, even if you're familiar with tracing already. So, what is tracing? Before explaining tracing, I want to talk about OpenTelemetry. OpenTelemetry mission is to enable effective observability by making high-quality, portable telemetry ubiquitous. Observability is this puzzle that you're solving, and OpenTelemetry gives you a lot of telemetry signals to solve the puzzle. Traces, logs, metrics, eBPF, profiles and snapshots in the future. All the telemetry signals helping you to troubleshoot and profile your application. Tracing is not a new concept. For years, people were recording beginning of request, processing of request, and returning the results. When we talk about tracing today, we refer to distributed tracing. These days, distributed tracing as a practice to profile and analyze code for modern microservices-based applications is everywhere. Because all applications are split by network and into multiple components. Let's go into the basics of tracing. Consider a simple call. Client talks to the server. When client sends a request to the server, then server processes this request and returns the result, and finally client makes a final processing of a request, of a response, and completes the operation. This collaboration can be represented with two bar charts. One bar chart on a picture that's bluish will represent client execution, and yellowish bar chart will execute server processing of this request. You may see the time difference between these two bar charts. This time difference represents networking call and client processing the request and response. You may see that in this example, the time difference is not that big. So it's not a latency problem if you investigate performance bottleneck. It's likely as a server doing something fishy to take whole 2 seconds to process the request. These bar charts we call span in OpenTelemetry. You can easily remember span by thinking about time span between begin and end of request processing. So in OpenTelemetry, span is more than just begin and end of request processing. It also consists of multiple attributes that represent and identify the specific span. We can start with a kind. Kind is talking about type of a span, whether the span represents something that goes outside of applications through the network, or server that represents span that processes the incoming request. It also may be internal span, just internal processing of something. A span may have some custom attributes, and then some attributes identifying using some well-known semantic that OpenTelemetry defines. These attributes may represent application that processing the span. It may represent where this application deployed, like cloud or process or instance. It's called typically resource. It also represents some HTTP specific attributes like URL or status code. Or it may have some networking information like IP of your peer and stuff like that. All this information is very valuable to identify the span, and it's important to have it standardized. This way, the person who is looking on telemetry shouldn't know about specifics of an application. It doesn't matter which language this application is written on, you know that it's HTTP call, and this HTTP call went to this specific URL. I will talk about importance of standardization later in this talk as well, but now let's talk about the relationship between spans. Multiple spans may be involved into processing of a single operation. In this picture, span starts with trace starts with a huge processing, huge time spent on processing on the server. We call it a root span. So the server calls into two clients. First time it calls into one server. Second time client calls into the second server through the network. First server may have another dependent service to call and some custom processing. And other server may have some call to external service, third-party processing, and initiate some maintenance operation that may be long-running and span beyond the initial trace execution. All the spans on this picture are connected by having this one trace ID. It's a piece of information shared between clients, server, across the network, everywhere. So having trace ID, you can see the shape of a trace, which spans, which services were involved into processing this operation, and how they stack together. To better stack them together, there is also a concept of parent-child relationship. It's when one span calls another span to execute, or links. Links may be between spans or maybe between different traces. When this trace initiated maintenance operation, long-running trace that connected to the original trace but not directly related to it. So now with trace ID, you have a power of defining the whole trace and knowing that all the spans for the whole trace. So you know the shape of a trace. If you have low volume request application, you may collect information about every single span. That's not too much information to collect. But if application has very heavy load, you may need to start applying some sampling. Without tracing, the sampling would be inconsistent and you wouldn't be able to see how individual request was processed across multiple components. Now, when you have trace ID, you can sample whole traces together. So let's say you have different types of operation: blue circles representing some default page rendering, red triangles representing some reporting page, and blue diamonds represent some ticker on the page that are updated very often. All the types of requests, if you pick randomly from all the requests, you will see a few examples of first, some examples of second, and many examples of third type of requests. And having these examples, you know the shape of the trace, and you can reason about whole category of traces and how they behave. But sometimes random sampling wouldn't work quite well. You need to have some more advanced sampling mechanisms. You may want to filter specific traces, let's say synthetic traffic. All the health checks that takes a lot of requests, but they is fast and typically uninteresting. You may have delegated sampling, the mechanism of delegating the sampling decision and such, or tail-based sampling. This is a very powerful mechanism that looks into entire trace, search for error spans. In this example, one blue span with a screaming face on it. And if it detects the screaming face, it will collect the specific example. This tail-based sampling as a generic solution across any application is only possible because OpenTelemetry standardizes the attributes we collect. So the screaming faces is not some custom attributes that you need to search for. It's some generic information about error or some attribute that defines the same way across languages and across frameworks. Also, having trace helps you with scenarios beyond just tracing. When you can propagate trace ID, you can also propagate more information, some custom labels. And these labels may help you with various scenarios like synthetic traffic labeling or fault injection, maybe to like traffic prioritization and quality of service scenarios. It's all possible because now for every single trace, you know every single request processing and piece of code that process specific trace. And it's all possible because OpenTelemetry respects standards. When you propagate something between networks, between different applications and different frameworks, you need to make sure that all components understand each other. They use the same format of propagating information. And that's where WC trace context, that is default propagation format in OpenTelemetry, plays a very important role. And with OpenTelemetry, you don't need to learn about this standard. You just need to use some helper methods. So in this example, I propagate information about current span, which is marked as client, through the HTTP headers. So I just call a simple inject method that will take information about current span, serialize it in a well-known format, and send it further to the server component through the HTTP headers. On the other side, no matter what language application is written on, it will extract headers using some extract command, and will continue span execution from there. On this example, I use an object called tracer, and Yoshi will introduce you to how the tracer works and what other concept OpenTelemetry gives you.
Thank you, Sergey, for the introduction of the concept and overview of OpenTelemetry for trace. So let's go deeper into its specifications and implementations. So these components in this diagram are what you need to instrument to propagate trace information from one service to another. Let's drill down one by one. The steps you need to follow is 1. To initialize tracer provider, and 2. To get a tracer from that tracer provider object, and 3. To create spans with that tracer. Usually steps for tracer provider and tracer are only required once during the initialization process. Tracer provider holds all configurations on how to handle trace and spans, such as sampling rates, how to send spans to the backend servers, and how to generate trace and span IDs, etc., etc. Tracer provider is also in charge of generating tracer. So tracer is the object that can generate spans with a context in the application. Span holds all context information of trace and context of span itself, such as attributes and events. Attributes is timeless properties, whereas event is the label with timestamp inside the span. Let's see this step in a concrete source code. This example is trying to send spans to Jaeger, a famous open source trace backend. So first, it creates an exporter object for Jaeger, and the exporter object is passed to span processor. The span processor object is passed to tracer provider configurations. And now, the tracer provider knows where and how to send spans. Also, this configures the sampling rate. In this case, all traces will be sent to Jaeger. Then, this tracer provider is set as global. Also, you set the propagator so that the tracer provider can be aware of how to propagate context. So that's it for tracer provider initialization. Next one is tracer. Getting tracer is really easy. You just need to get tracer object from tracer provider with tracer name. Tracer name is usually the label for a set of spans in the service. And this is the most interesting part, span creations. Now you have a tracer. You can generate spans as much as you need. You need to be aware on how context object is handled here. Inside the service, the context object holds all trace information and state, so you need to be careful about it. By assigning a proper context to the tracer start method, the context can keep proper relationships in it. After instrumenting all required spans in the program, you will see this kind of insightful waterfall chart on your Trace backend UI.
Yeah, Yoshi, I noticed that in your code example, you skipped the part when labels got populated. And as we demonstrated earlier, there are a lot of labels that needs to be collected. So it results in many concepts that you need to learn and many data you need to collect just for easy getting started. What do you think about it?
Yeah, I agree. Instrumenting all by yourself manually is really hard work. But nice thing is that OpenTelemetry ecosystem provides powerful libraries that empowers you to instrument the app with less effort. One of them is the Auto Instrumenter. Imagine that you are trying to instrument Web API server, and you just need spans at the root of each handlers. What if some libraries automatically instrument spans with required information on behalf of you? This is what Auto Instrumenter does. In this sample, someone is trying to instrument Web API server with Flask, a Python framework. Please look at this line. This line does a lot for you. Flask Instrumenter instance automatically injects root spans in each handlers. And in the handler function root, you don't need to write a root span, as we did in a previous example. Of course, if you want to add child spans in it, you can do it as normally, like these lines. In this waterfall chart, this root span is automatically generated one, and also the subspan is handwritten child span under the root.
Yeah, and I see all the standard attributes, HTTP method, URL, all this interesting information automatically collected on behalf of you. This is great.
Exactly. This is the demonstration of how powerful Auto Instrumenter is. So let's review the code in an end-to-end example and how it will be visualized on Jaeger. Okay, let's review what we have done in the slides with this simple client and server example. This client is implemented in Go, and the server application is implemented in Python. First, client application creates Jaeger object, which is for exporter, and register that exporter object to spam processor initialization. Now you have spam processor object, you can create tracer provider with it. Also, you can set up sampling rate and resources, and so on. Now you have tracer provider object, you can set that object to global. Now you have tracer provider object in global, then you can get the tracer object with the tracer method. Here, you can get the tracer object named client. With this tracer object, you can create as many spans as possible. So, you are creating the root span named client root here. In order to confirm the trace ID, I'm printing it out here. Also, because this is the client application for the server, it calls HTTP request. So I'm creating child span to track the latency of the HTTP request. So this child span is named API request. In order to confirm the trace ID is propagated successfully, I'm printing it out here as well. And now this program is calling the server endpoint with customized client HTTP client. And the last line is printing out the response body. Let's review the server program. The server program is mostly the same in terms of the instrumentation. The only difference is that this Saba program is using auto-instrumenter for Flask. So this line, Flask instrumenter dot instrument underverb up, is injecting the auto-instrumenter for application object for Flask. The other process is the same as the Go program. So create the exporter object first, and then register it to the span processor, and pass that span processor object to the tracer provider initialization, and register that tracer provider to global. Same. The highlight here is that the handler is not instrumented for the root span. Though you see some span instrumentation, this instrumentation is for a subspan or child span under the root span of this root handler. And this root handler is embedding the trace ID, which is propagated from the client object to the response body. Let's see how it goes. So the Saba program is already up, so let's run the client. As you can tell, the same trace ID is propagated from the client root to the server. And you can confirm that in Jaeger traces. So this trace is just generated. As you can tell, the same trace ID is propagated through the client to the server, and you can confirm all spans you generated manually and automatically. As you saw in the demo, auto-instrumenter is handy, but I can show another great tool for you. So SQL Commenter is another powerful library in the OpenTelemetry ecosystem. So SQL Commenter project recently joined OpenTelemetry. By using SQL Commenter and its compatible backend, you can easily correlate database queries with traces. By visualizing the query latency information along with trace, you can capture slow query at a glance, for example. What SQL Commenter does is straightforward but powerful. It intercepts the query via OR mapper or database driver, and it injects trace context information into SQL query as the comment.
Great, so it's even better than automatic instrumentation. You offload generation of spans to the cloud, and all the context is propagated using small library. This is great.
Yeah, it is. So you can analyze the queries just only with the database SQL, as well as if you use the compatible backend, you can visualize whole trace information on the waterfall chart. So there are a lot more to tell you about OpenTelemetry for trace, but time is up for today. We hope you will enjoy instrumentations with OpenTelemetry. Well, thank you for joining today, and if you have any questions, please reach out to us.
Thank you. Bye.
Bye.